Hello everyone, welcome to clip 3 of ROS for beginners. In two previous clips, we talk about introduction for ROS to get more familiar with the basic of the robot operating system. In this video, we are talking about Xacro file, how to create a Xacro file, how to describe our robot in the Gazebo simulation. Uh, we'll discuss about what is the Xacro file, how to create a Xacro file, what's the Gazebo, and how to create a Gazebo, how to launch file for the Gazebo, how to implement our robot inside the Gazebo environment, and we will conclude our content. Okay. Xacro file, which is written in XML coding format that describe our robots. We can define our components of the robot, such as link and joints. We can add different type of sensors also, like camera, laser, and other sensors. So is a Gazebo is a physical simulation. We can describe our robot, multi-joint robot, mobile robot, even drones. There's some physical features there that is similar to the actual environment. Also, we can monitor the joint movement uh, and sensors. We can visualize and we can see the influence of the world inside our sensors. Also, we can implement our different worlds inside our Gazebo environment. So for this video, I just prepared some one example, which is a mobile robot have 4 wheels and 1 body. Uh, um, I will create a package for the robot, and I will describe the Xacro file, and I will create the launch file for it. So let's go and start. For this example, I just provided one mobile robot already created, and you can download from my GitHub. I will share the link in the description. If I forgot, please comment and remind me, please. Okay, so in this file, if you click, we can see we have launch file and URDF file. In the launch file, of course, is a launch file for the Gazebo, and for in the URDF file, we have the URDF. We can define our robot in two different formats, Xacro and URDF. I will describe what's the differences. In this case, I think I defined in the URDF file, that URDF, and you can see URDF file inside the GitHub. Let me start with the downloading the GitHub file. You can download in the two different ways. You can download zip file, or you can copy here and download and use in the terminal. In this case, I'm going to create a new working environment, ROS working space. So I just create a direction. I call it Catkin WS for YT. Then I have to go inside the created direction WS underscore YT. Sorry, I made a mistake. CD. Then I have to create source file src, then make a catkin compiled already. As we can see, the build, devel, and source already is created. Okay, in order to download the GitHub package, the package from the GitHub, I mean, we have to go to src. Then we can type git clone and paste. It's cloning and already downloaded. We can see the package is already there, mobile underscore robot, and we can go inside it. Mobile robot, again, as you can see there, again mobile robot. You can see the launch file and the URDF. Okay. Okay. In order to compile the package that downloaded from GitHub, we had to compile it again, because it's, if we don't compile, it's not written. It won't be written in the build and devel file in here. Okay, so we catkin again. Whenever you download any package from GitHub, you have to recreate your package. So it's already there. We have to source this first, or catkin ws underscore sorry, source devel stop underscore dot bash, then ROS launch, sorry, ROS launch mobile Gazebo, right? So mobile robot, the name was mobile robot. Press tab 2 times, then I will appear, and it is already there, right? Okay, so we are going to at the end of this video, we will be able to make this launch file. Okay, just kill this Gazebo, then we start to create our own package step by step. I try to make this video hands-on, more hands-on, so I just wanted to show you a demo. That's what we are going to make in this example. Okay, we go here, then in the URDF file. Okay, we will have this URDF. I just explained the URDF first. What we run just now, it was this URDF file in the Gazebo. So we will check one by one which component we have. We have link in here, which is our base link that the other wheels is connected to. So this base link join is a virtual, this one, the link is a virtual join, that this base join, the main body of the robot, connected to this virtual join through this joints, which is the fix. Okay, which is the fixed joint. The other our other links is the wheels, that we have wheel 1, which is connected to the base link, so through the continuous type of joint. Continuous type is continuously rotate 360 degree, right? You can see in the joint we will have parents and child elements. This parents and child means this joint, this link, which is the wheel, is connected to its parents that which is the base link, the body of our mobile robot. Same pattern for wheel 2, wheel 3 and wheel number 4. Okay, connected continues. In this part of this URDF, we describe the joint material, which is the color of our for the visualization in the gazebo. The color, for example, the base link is red, our wheels are green, right? And this is the transmission for the links, means this joint is going to move, right? And also here is a plugin for differential robot, mobile robot in the gazebo. So in this case we define over 4 wheels here, which is connected to the odom link, right, which is a virtual link, and it's going to rotate our wheels to push the mobile robot forward or backward in the gazebo environment. Okay, so we try to go going to our Cat King workspace that we just created. Okay, going to our source file, we just make a cat king to create a package. We can cat in create package. In this case we can name one package, like for example mobile underscore YT. Just create this package. It's already created, we can see it is already there. Okay, we go inside this mobile YT. We make a URDF file. This is the name of this folders I'm creating is doesn't matter actually. You can make a one package and you can just provide so many you can create different files with different names. So I just create the URDF and I will make the launch file. Okay, launch, this is 2 folders. Okay, here we can see our folders, URDF and the launch file. I will go to URDF file folder and I will create gedit. I use gedit, so any other text edit application, or usually people use Visual Studio Code, but I don't have Visual Studio Code here, so I use gedit and the name I will put, for example, mobile dot URDF. URDF and Xacro both will work in this case. Okay, this I can copy paste from my previous URDF file in the Github, but I want to go through it step by step. So we will have this file, the XML file. This line will show that this is the XML file. After that, we have to define our robot name, which is in this case is the name is a robot. Anytime you just open one line like this, you have to close it in blue, right? Make it robot. Okay. So inside it, so all the our other codings will go through between these two lines, which is the first one is a robot, and the second line is a robot, and the last line should be this robot. So all the name of the robot is defined in here. Okay, so we will define. Okay, just put here. I have at the same time. Okay, we define our virtual link, which is the link, and the name of the link will be base footprint. Any name you can define by yourself, but footprint is a common name that people use for virtual. I forgot to put the quota. You just press Ctrl C. When you save, you can see the line change because of this line. From this line, so the editor will understand that this is XML coding. So after that, we define our base link. So in base link, we have our visual. Okay, that we define the color, this material color, which is blue, and we define the size of the robot, which is 0.2 meter to 30 centimeter to 10 centimeter. And you can define his orientation. Orientation means where the robot will be located. In the middle of the gazebo is a 0, 0, 0, and this is roll pitch yaw and XYZ. You can define the position of your link, and also is a collision. Collision is for gazebo. You can this visualization. This is the collision of your robot. Inside it, you can also define the inertia matrix. This is inertia matrix IXX, and these three elements are important: IXX, IYY, and IZZ. So how to calculate is a mathematical formulation for it. You can calculate, you can search and find out how to calculate it. It's defined based on this size that you define and the density of the material that you choose. For example, in this case, I define the aluminum, I think. And here we close our link. So this, from this link which define the name, which is the base link, to the end is definition of our body of our mobile robot. After that, we have to define our wheels, right? Same thing, this is the wheels, and we define the description here, description of the wheel inside this link, which is the type is the cylinder. Here was the box, here is the cylinder, right? Because it's a wheel, right? And the length and the radius of it, the height and the radius, the color, the origin of it, which is 0, 0, 0, and the dimension and the inertia matrix, and the mass. We can define the mass also. So right now we already have two links, but these two links should be connected to each other, right? So we will have this join. Okay, in the join we have the name of the join, the type of the joint, and child and parents, and the axis. In the axis is X, Y, and Z, right? It show in which direction should this joint rotate. in the X direction, in the Y direction, or in the Z direction. Okay, so we just gonna save this over URDF. Okay, we want to check our URDF that is so far is okay or not. So we are in the right direction. We type check underscore URDF if not mistaken, and the name of it fail. You can see the fail to find root, 2 root links found, and base link, and okay. The problem is I forgot to connect this base footprint and the base link. Here said I found 2 root link, which is over the, I said the virtual link, right? It's a root link. So I just copy paste here that I connect the base link to the footprint. So base link is connected to the footprint, the will1 is connected to base link. So try, it's okay successfully. So you can see the child of the footprint is a base link and the child of the base link is a will1. So we will go the same pattern for will number 2. Okay, this we describe the link. Okay, and then we define the joint, which is the same, exactly the same, only the position is different. So here I 45. So this the origin of the link here is the origin is a position of the joint. Okay, this position of the joint can be defined based on the calculation of the dimension, the geometry of our robot that we are creating. Okay, so we check again. Successfully, you can see the will2 is appeared already as a child of the base link. Okay, same scenario for base will number 4, number 3. Okay, and the same one for will number 4. We check it again, so you can see our links are connected, how the structure of our links. Okay, also we can define the material, the color of the links. Okay, then we can define the transmission. We just let's copy all because to make it until here. Okay, so because this is the URDF file, I have to copy everything in the United file. So it means I can have one file for description. Later, after at the end of this video, I will describe what's the difference between URDF and Xacro file. This format, as you can see, is the URDF file. So I should have one. I have to copy all the material description, everything in one folder. Okay, I forgot to copy this one. And the transmission. See, in the transmission we define the joint name. Okay, we define that which is the velocity control for this joint. We repeat it for other 3 joints also. Okay, if you don't have this transmission over robot won't move in the Gazebo environment. Okay, so far let's later I will go through this Xacro file, this URDF file. We will complete it. Right now I want to see how it's going to be if we use in okay. Okay, I came back from the short pause. I was looking for the launch file for the Gazebo, for the RVIZ. So far we already created our Xacro file, URDF file. We describe our robot and we could successfully compile it. Okay, we check our URDF file. Okay, right now I want to try visualize it in the RVIZ. So RVIZ is a tool to visualize our URDF and our sensors. If for example you have let's say you have a camera, you can visualize it, and let's say you have you have laser, for example laser sensor, you can visualize in the RVIZ. In our case we want to visualize our created URDF file. So we have to create a launch file first. So I go to my launch folder first, then again gedit to open a RVIZ launch file. Okay, so we try to create a launch file for RVIZ first, then we try to actually call our Xacro file, our URDF file. So first of all we call the launch. So we can create our launch file like this. Okay, save it. Then inside the launch file, if I let's say I just run it, so ROS launch mobile. Okay, so it's similar to the ROS core, right? Is create a master for us. If you make a empty text file, we just type these two lines, launch and close the launch. So you can see we can run the ROS core, the master. It's similar, but inside this master that we already create our master, right? I want to call my robot. Okay, let's copy here. This is the argument that call our model. So we can use in this case, or we just directly from this param call our the name of the robot, which over file here. This one, the command launch the Xacro file, which is the predefined package in the ROS to call our Xacro or URDF file. Okay, here the Xacro file find the our package, which is mobile underscore YT. Okay, inside it there is a URDF file, and inside the URDF file, what's the name of our URDF is a mobile URDF. Let's run it. If I okay we already implemented our URDF file in the launch file. So let's run it. What happened? RVIZ, okay, it's already run in the separated terminal. Type RVIZ and just run it, and you can go add. This is the environment of the RVIZ. Okay, you can go to the add on the left side, and you can see different topics, different features for visualization in RVIZ. But in this case we need only robot model. Okay, just click OK, then you can see the body, the frame body. So here you can see the error that our links are not connected to each other, right? So also if I click the fixed frame, I cannot see over my links, right? And these are not connected to the map which is this one. Okay, we just close it. Okay, just close it and try to add this line that describe the TF for the our robot model. This package called the TF. TF is describe how the robot links are connected to each other, right? Then I try to run it again. Let's see. Here I can select the best link, and you can see these are, you can see here. Okay, so I can see the base footprint and the base link, but still the wheels are not connected, because the wheels are the continuous type of robot, right? This one, the link the joint link, these are fixed. The fixed joints can be recognized, but the continuous joint, it cannot be recognized. So we need the joint state publisher package. So we create another node. Okay, then we create another node. Okay, for the node we need name, we need package, and we need type. Okay, in the name, which is joint state publisher, J is not capital, joint state publisher. Okay, we define this name and the name of the package, and the type is similar. Paste and save. Okay, let's try it. Okay, you can see join the state publisher node in here, and robot state publisher node. Okay, and go to the RVIZ, select the robot model again. Then you can see the 4 wheels. If I select the wheels one, and you can see the created model, everything looks good. The wheels are here connected to the body, right? The wheels are here. This is the model that we want to implement. We already created, and we are going to implement it in the Gazebo. Okay, so far everything looks nice. close it. Okay. Okay, we come back to our URDF. After running in the RVIZ, we are going to run it in the Gazebo. For the Gazebo, as I mentioned, we need this transmission to activate our joins. Okay, and later we need this package with this plugin for move over robot. Okay, we try to create the launch file first, then we will try to move over robot in Gazebo. Okay, first we implement first. We are in the launch file. We ls, which is the RVIZ.launch. Again, gedit. We want to make a Gazebo launch file. I just selected the name Gazebo. Okay, again, similar to creating a launch file for RVIZ, we just make it as a launch file. We create our master to implement the programming. Okay, in this case, in the launch file creating for the Gazebo, we have to include the wall. Here I implemented the empty wall. Later I will describe how to implement different kind of the wall at the end of this video if I don't forget. Okay, so this is the empty wall. Okay, so if I launch it, ROS launch, only launching this empty wall. ROS launch, what's the name is mobile.yt, then our case is gazebo.launch, right? See, you can see this Gazebo is pop up, but it's empty. It's an empty wall, so there is no robot in it. So after this, we try to implement our robot description. Okay, same as RVIZ. This is our robot description. It's calling from this package, this URDF. Okay, we run it again. Okay, still it's empty. Why? Because we haven't described the spawn model. So we just created spawn model. We call the URDF. The name of the model is here, and this is the here we can modify the position of it. So we call this package. In this we create a node and we call the Gazebo ROS package. So we try to run it again. Compiling, and we can see our model inside the robot is not stable. We have to find out why. This do not look like stable. Okay, I think we have to check. The position of the. Okay, we check position of the joints. So let me check first, then I'll come back. Okay, I have checked the mobile robot. Here the position, the orientation of the right wheels are 45 millimeter. Here is 45, but here is a 60. So we change it to same value for all of them. 06, sorry, zero 6, right? 06, not 006. Okay, and this one 6. Okay, it's supposed to be nice and stable, hopefully. Okay, looks good, stable. This is stable. Okay, we can open another terminal and check over, sorry, make it bigger, check over topic or topic list. Okay, you can see the Gazebo link, Gazebo model, but we want to move our robot, right? Okay, I came back after a short pause. Okay, we just described our your robot in the RVIZ and Gazebo. Now we are going to move it in the Gazebo environment. So we need this plugin. So this plugin for the differential robot to move them, you can see that we define 4 wheels here. The name of the topic will be CMD underscore well command velocity, and it will be the plugin for the differential robot. Okay, for more information you can go to Gazebo plugin wiki. Then you can see the different type of plugins like camera, laser sensor, GPU or laser sensor, and you can see the IMU and this differential robot. I took this plugin from this description. Okay, so we run the robot again one more time. Okay, she's in here. We run the ROS topic list, and you can see the CMD well here. So for running the robot, I run the ROS run turtle 03 off. You can this one, the key, right? So you can see that with the keyboard WSD X and A I can control it. So you can see the robot is moving around. Okay, so also you can see the RQT graph. You can see the connection of the Gazebo with the turtlebot lobe through the CMD well. So these nodes are connected together with this ROS topic. In the previous clip it described the ROS topics, then how they are communication, what's the meaning of the ROS node and ROS topic. You can watch the clip number 1, I think 1 or 2, in both of them I described. You can see in my YouTube channel both clip about the ROS topics. Okay, anyway, this robot is already moving in the Gazebo and it's moving around. Just we press C2. Okay, we can control the robot. Okay, right now two things I'm going to mention that I said in the middle of the video talking about the Xacro, difference between Xacro and URDF file. In the Xacro file, if I find the Xacro example here, for example, it is the Xacro file. Okay. In the Xacro file, we can separate our description and calling them like this, that go to this, for example, mobile description URDF, this is the different package, call the material and the mobile. Okay, then this continue describing our robot. Okay, what is inside these two materials and gazebo that mentioned here? This is the direction in the in the material we describe the colors of the robot, of the links. Okay, and in the Gazebo file I just describe the different plugins for the robot. In this case, if you have the URDF format, describe your robot in the URDF format, you cannot describe the Xacro file in the separate format. But if you use the Xacro file, you can separate it. And there are other features that you can search in the ROS Wiki URDF. The other thing that I'm going to mention is the TF, checking the TF of the robot in Gazebo. I forgot to mention. So one more time, running the Gazebo. Right now I'm going to show you how to check the description of the robot. We already checked the description of the robot with check URDF, right? So in this launch file, run ROS, run, then RQT. With this command you can check you can visualize the connection of the links to each other. So you can see these joints are connected to each other. Okay, and also another way, which is the TF underscore view frames. In this case you can download the TF file as a PDF. Why not? Which is something similar to this RQTTF3. Okay, you can save it and you can monitor your robot links together. Okay, just kill this ROS server. We conclude our video. For the conclusion, we learn how to create the Xacro file. I mean, how to describe. We learn how to describe our robot in XML for robot operating system. Also, we learn, we get familiar to the launch file, how to create a launch file, how to implement our robot in the RVIZ and Gazebo, how to apply the plugin. We just have one plugin, but you can add more plugins, and it maybe in the future I make a one video about how to add the different plugins and how to visualize them in the RVIZ environment, for example camera, depth camera or laser. Follow me, I will make a short video about that. And in the next video, which will be clip number 4 and 5, we will try to apply the slam or navigation. Slam for first we have to add the laser first, then we have to make a map in the Gazebo environment and navigate over robot autonomously. Thank you for watching this video. Please subscribe my channel and like this video. If any question, please ask me in the comment. This video was a hands-on video. I try to compile and run my program real time, so you could monitor everything my screen while I was running the program. Thank you very much for watching this video. See you later.